In the depths of the Milky Way, there is a region where the cosmos seems to be in a state of continuous birth. Here, cold and red-hot plasma, absolute darkness, and blinding radiation exist simultaneously, creating a grandiose picture that has been going on for millions of years. Among the dense clouds of interstellar gas lies one of the most famous and at the same time the most mysterious nebulae of our galaxy, M16, the Eagle Nebula. Its radiance looks calm only from afar. In fact, inside this giant cloud, processes are constantly taking place of such power that they completely change the surrounding space. Gas structures stretch for many light years, new stars are born, ancient clouds of matter disappear, and powerful ultraviolet radiation gradually rebuilds the entire region. Each region of this nebula bears traces of events that began long before the modern structure of the Milky Way appeared and continue even now, turning M16 into one of nature's most important laboratories for star formation. The Eagle Nebula is located about 7,000 light-years from the solar system in the direction of the constellation Serpens. Its size reaches tens of light-years, and the mass of the matter contained inside is many thousands of times greater than the mass of the Sun. Despite its beautiful name, it is not a single object, but a huge complex of cold molecular gas, dust, young stars, hot plasma, and regions of intense star formation. All this is united by a single origin story, which began inside a giant molecular cloud. Such clouds exist in almost every major galaxy. They consist mainly of molecular hydrogen, a small amount of helium, and many heavier chemical elements formed in previous generations of stars. The temperature inside the densest regions can be only a few tens of degrees above absolute zero. It is these cold conditions that allow the gas to gradually condense under the influence of its own gravity. However, cooling alone is not enough. A huge cloud can exist for millions of years with little or no change, until its equilibrium is disturbed. The cause can be shock waves from distant supernovae, collisions of gas streams inside galactic arms, pressure from nearby hot regions, or the cloud's own instability. After that, a slow but irreversible process of collapse begins. In some areas, the density of matter becomes higher. Gravity gradually intensifies, causing the surrounding gas to flow to the center of future stars. As it shrinks, the temperature increases. Dense protostellar cores are formed, surrounded by rotating disks of matter. This is how the life of new stars begins. The M16 is one of the most impressive examples of such a process. Dozens and hundreds of objects of different ages exist here at the same time. Some are just beginning to assemble from cold gas. Others are already heating up so much that they begin to emit infrared radiation. Some have entered the stage of a full-fledged star, and the most massive are already beginning to destroy the cloud that once gave birth to themselves. The main feature of the Eagle Nebula is the constant confrontation of two fundamental processes. On the one hand, gravity tries to collect matter into new stars. On the other hand, already formed massive stars destroy the surrounding cloud with their powerful radiation. This radiation consists mainly of high-energy ultraviolet photons. They collide with gas atoms and deprive them of electrons. The process of ionization occurs. Huge areas of the cold molecular cloud turn into incandescent plasma with a temperature of about 10,000 degrees. Such plasma begins to expand, gradually pushing the remnants of cold matter outward. At the same time, stellar winds are at work, continuous streams of charged particles moving at speeds of hundreds and even thousands of kilometers per second. They literally blow cavities inside the cloud, creating giant caverns, arcs, and complex fibrous structures. That is why the Eagle Nebula has such an unusual appearance. It is not a stationary cloud. Each of its parts is constantly changing. The most famous area of M16 was called the Pillars of Creation. These giant columns of cold gas have become one of the most recognizable images of modern space. However, their appearance is deceiving. They appear to be monolithic formations, but in reality, they are extremely fragile structures that are constantly collapsing. Each of the pillars is a dense remnant of the original molecular cloud. The increasingly less dense matter around them has already been carried away by the powerful radiation of young stars. Denser areas were able to resist this impact for much longer, forming giant, elongated columns several light-years long. Their surface is constantly subjected to photoionization. Ultraviolet light heats the outer layers, causing the gas to gradually evaporate into the surrounding space. This process is called photoevaporation. It has been going on continuously for hundreds of thousands of years, and over time, it will completely destroy the pillars themselves. However, it is within these gradually disappearing structures that new stars continue to be born. In the densest nuclei, the gas remains cold enough for further gravitational compression. Thus arises a wonderful paradox. Destruction simultaneously becomes a condition for a new birth. Even the smallest dense clumps inside the pillars are able to persist much longer than the surrounding substance. They become a kind of cocoons that hide the earliest stages of the formation of future stars. They cannot be seen in the normal visible range, since dense cosmic dust completely blocks light. Only infrared radiation is able to penetrate these dense veils, revealing the complex internal structure of the Eagle Nebula. It turned out that there are many more young objects hidden inside than could be assumed from ordinary photographs. Many of them are surrounded by rotating disks of gas and dust, from which planetary systems can subsequently form. This means that M16 is not just a star cradle. Here, future worlds arise at the same time. The processes of planet formation begin almost immediately after the birth of a star. A rotating disk of matter remains around the young star. Dust particles collide with each other, gradually increasing in size. Then there are kilometer-long bodies that continue to merge. Over millions of years, full-fledged planets appear. But the conditions inside the M16 are extremely harsh. Radiation from nearby massive stars can completely destroy the protoplanetary disk even before its evolution is completed. Therefore, not every young star has time to form a full-fledged system of planets. Some future worlds may disappear before they are finally born. This is what makes the Eagle Nebula particularly interesting for understanding the origins of planetary systems. It shows how diverse the conditions for their formation can be, and how much the environment influences the further evolution of young stars. At the same time, M16 helps to understand the origin of chemical elements. The gas inside the nebula already contains carbon, oxygen, nitrogen, silicon, iron, and a host of other atoms. They did not appear here initially. These elements originated within older generations of stars and were ejected into the interstellar medium after their demise. A new generation of stars inherits this material and then returns it to galactic space, supporting an endless cycle of cosmic evolution. As the inner regions of the Eagle Nebula become more transparent, another feature of its structure is revealed.
It is not a chaotic cloud of gas, but an extremely complex system in which every movement of matter is connected to dozens of other processes. Streams of incandescent plasma collide with cold molecular clouds, creating shock fronts that extend for many light years. Where such a wave passes, the density of the gas increases dramatically. Sometimes this leads to the destruction of existing structures, and sometimes it is the beginning of the birth of new stars. Thus, the nebula itself gradually rebuilds its internal architecture, constantly changing the location of star-forming regions.
The boundaries between cold and hot matter are especially interesting. Thin transition layers arise here, where the temperature can change by thousands of degrees in just a relatively short distance on a cosmic scale. Gas is in an extremely unstable state. Any small change in density or pressure begins to intensify, forming new fibers, clumps, and tortuous structures. That's why the M16 photos show such an unusual network of intertwined clouds that resemble living matter, even though every curve is based on the laws of physics. Within the nebula, there is a continuous exchange of energy between matter and radiation. Each high-energy photon is capable of changing the state of the surrounding gas. It knocks electrons out of atoms, triggers chains of collisions between particles, heats up clouds, and alters chemical reactions. Even a slight change in the intensity of radiation gradually affects the fate of huge regions of the nebula. The cosmos here turns out to be surprisingly sensitive to the most seemingly insignificant changes in conditions.
Magnetic fields work at the same time. They are virtually invisible, but they have a huge impact on the evolution of M16. Charged particles cannot move freely through magnetic lines. Instead, they begin to follow them, forming elongated streams of plasma and thin fibrous structures. Magnetic fields can slow down the contraction of gas clouds, change the direction of material movement, and even affect the rate of new star birth. The question still remains how great the role of these magnetic fields in the formation of the famous pillars remains. Some features of their structure cannot be explained only by the influence of gravity and ultraviolet radiation. There is a possibility that it is the magnetic lines that keep some of the matter from breaking down rapidly, allowing the columns to exist much longer than expected. If this is true, then inside the Eagle Nebula, there is another important mechanism for the formation of cosmic structures, which is not manifested in all regions of the galaxy.
No less mysterious is the internal turbulence of clouds. The gas inside the M16 is never at rest. It is constantly moving at different speeds. Some streams collide with each other, others diverge, and still others twist into giant vortices. The scale of such movements is measured in tens of light years, and the speed of individual flows reaches tens of kilometers per second. These motions gradually redistribute mass within the entire nebula, determining where future stars will appear and which regions will forever remain empty. Turbulence both helps and hinders star formation. If the movement of gas is too intense, the cloud does not have time to shrink under the influence of its own gravity. But if the turbulence begins to fade, the matter quickly concentrates into dense nuclei. A kind of balance between chaos and order is obtained. It is thanks to this balance that both regions of active star production and vast spaces where this process has almost completely stopped can exist within one nebula.
Particular attention is drawn to the so-called globules, small, dense clumps of cold gas scattered throughout the nebula. Their size is much smaller than the famous pillars, but it is in them that the youngest star embryos are often hidden. The density of matter inside such objects is so high that external ultraviolet radiation is not able to immediately destroy their internal structure. They become the last refuges of cold gas among the red-hot plasma. Some globules have an unusual shape. Their elongated tails always point in the opposite direction from the brightest young stars. This is the result of the continuous pressure of radiation, which literally blows away the outer layers of the gas. Such formations exist for a relatively short time by cosmic standards. In a few 100,000 years, most of them will disappear completely, leaving behind only new stars or scattered clouds of matter.
Inside M16, you can find numerous shock waves that occur when stellar winds collide. When two powerful streams of plasma meet, the energy of the collision is converted into heat and radiation. The gas begins to glow even brighter, and its temperature rises to millions of degrees. Such regions become sources of X-rays, indicating the colossal energy processes hidden behind the nebula's calm appearance. These high-temperature areas play an important role in the redistribution of energy within the entire complex. Hot plasma expands faster than cold gas, gradually pushing matter outward. Over time, this leads to the formation of giant bubbles, inside which the density becomes significantly lower than the surrounding environment. Such structures gradually merge, changing the shape of the entire nebula. Even the chemical composition of different parts of M16 is not the same. Some areas are richer in oxygen, others contain more sulfur or nitrogen. These differences allow us to trace the history of the formation of individual parts of the cloud. Denser regions are able to retain their original composition much longer, while open regions blend more quickly with the surrounding interstellar medium. As a result, the Eagle Nebula gradually loses its original structure, becoming part of the general matter of the galaxy. Interestingly, the birth of massive stars simultaneously limits the emergence of subsequent generations. The more young giants appear inside the cloud, the stronger their destructive impact becomes. After a while, the intensity of ultraviolet radiation reaches such a level that there is less and less cold gas left. At some point, the formation of new stars begins to slow down and then almost stops. A peculiar mechanism of self-regulation is obtained. The star-forming region itself creates conditions that gradually complete its own activity.
This process determines the fate of almost all such nebulae in the universe. They don't last forever. Their bright phase takes only a short period of time compared to the life of the galaxy itself. In a few million years, M16 will no longer look the same as it does today. A significant part of the gas will dissipate, the pillars will disappear, and a young star cluster will remain in place of a dense cloud, surrounded by a much more rarefied interstellar medium. But even after the disappearance of the nebula itself, its history will not end. Young stars will continue to exist for millions and billions of years. Some of them will acquire their own planetary systems. Others will be so massive that they will complete their evolution with grandiose supernova explosions. Then, the heavy chemical elements will be ejected into space again, becoming the building material for the next generation of molecular clouds.
Thus continues the endless cycle of cosmic evolution. A cloud gives birth to stars. Stars destroy the cloud. The remnants of matter become the basis of a new cloud, from which new luminaries arise again millions of years later. The Eagle Nebula is one of the most visible manifestations of this grandiose circulation of matter, which has been going on for almost the entire history of the Milky Way. However, even such a large-scale picture remains only a part of what is happening inside M16. Behind the bright clouds and shining areas, there are processes that cannot be seen directly. Many of them occur deep in dense areas of dust that are completely closed to visible light. These regions appear as dark silhouettes only because the dust inside is extremely efficient at absorbing radiation. Each microscopic particle is made up of compounds of carbon, silicon,
oxygen, and other heavy elements. Despite the tiny size of the individual grains, their total number is so huge that they are able to completely hide entire regions of star formation.
It is in these opaque clouds that the youngest objects of the Eagle Nebula are born. Inside dense cocoons, the temperature remains extremely low, and the pressure gradually increases. Gravity slowly pulls matter toward the center of future stars. Compression continues for tens and hundreds of thousands of years. The gas becomes denser, the inner regions begin to heat up, and the rotation intensifies. Even a small initial movement of matter gradually turns into a rapidly rotating disk surrounding the nascent star. Part of the gas from such a disk falls to the central core, increasing its mass. The other part begins to move along the magnetic lines and is ejected outwards in the form of narrow jets of matter. These colossal streams are capable of extending for many light years. They break through the surrounding cloud, creating long channels and shock fronts that become new sources of turbulence. Thus, even a star that has not yet completed its formation is already beginning to actively change the surrounding space.
The speed of these jets reaches several hundred kilometers per second. Colliding with cold gas, they heat it to high temperatures, causing the glow of certain parts of the nebula. Such ejections exist for a relatively short time, but they make it possible to trace the direction of rotation of young stars and understand how the redistribution of matter within protostellar systems occurs. Space dust plays an equally important role. Although its mass is only a small fraction of the nebula's total matter, without it, the modern process of star formation would look very different. Dust particles effectively cool the cloud by emitting accumulated heat in the infrared range. Thanks to this, the gas is able to continue to compress. If such a cooling mechanism did not exist, the temperature would quickly stop further collapse of matter, and the formation of most stars would be impossible.
Complex chemical processes also take place on the surface of these microscopic dust grains. Molecules of water, carbon monoxide, methanol, ammonia, and many other compounds are formed here. Some of them become the basis of even more complex chemistry that develops already inside protoplanetary disks. Thus, chemical evolution begins long before the appearance of full-fledged planets. Each new star changes not only the surrounding gas, but also the chemical composition of the entire region. Fluxes of high-energy radiation destroy molecules, creating new combinations of atoms. At the same time, shock waves mix different regions of the nebula with each other. Over time, the substance becomes more and more homogeneous, but this process is never completely completed. Even after millions of years, regions with different temperatures, densities, and chemical compositions persist within M16.
One of the most unusual features of the Eagle Nebula is the huge variety of young stars. There are objects with a mass only slightly higher than the mass of the largest gas planets, and real stellar giants are formed nearby, surpassing the Sun by dozens of times. Such diversity arises due to the different densities of individual regions of the original molecular cloud. Where there is a lot of gas, the most massive luminaries are born. Less dense regions give rise to much more compact stars. It is massive stars that determine the fate of the entire nebula. They are extremely bright, incredibly hot, and use up their fusion fuel reserves at a tremendous rate. Their lives last only a few million years, a blink of an eye compared to the existence of less massive stars. But in this short time, they manage to completely change the surrounding space.
Powerful radiation literally carves giant cavities inside the cloud. The pressure of light and stellar winds accelerates matter to enormous speeds. The gas leaves the central regions, gradually dispersing throughout interstellar space. With each millennium, the Eagle Nebula becomes less dense. Its original structure is slowly disappearing, giving way to a young star cluster. But this process cannot be called destruction in the usual sense. Rather, this is another stage of evolution. Matter only changes its state. Gas becomes stars. The stars recycle the lighter elements into heavier ones, then return them back to space, where the next cycle of new object formation begins. In the universe, almost nothing remains unchanged. Even the most magnificent nebulae are only a temporary stage in the continuous motion of matter.
A special mystery is created by the fact that the real size of the internal processes significantly exceeds what can be seen in the images. The light leaving different parts of M16 is born in conditions that differ from one another by many thousands of degrees. Some regions emit a predominantly red glow of ionized hydrogen. Others glow brightly due to oxygen, and still others to nitrogen and sulfur. The aggregate of these lines forms a complex map of the physical conditions within a nebula. If the human eye could perceive the entire range of electromagnetic radiation, the picture of M16 would look completely different. In addition to the usual light, incandescent regions of the X-ray range, cold dust clouds shining in infrared light, powerful radio-emitting structures, and numerous streams of matter permeating the entire nebula, a constantly changing system would appear before your eyes, where there are practically no stationary objects. There are signs that the very first fragments of future star clusters are just beginning to form inside some dense clouds. So far, they are completely hidden by a thick layer of dust. They cannot be seen in detail, but the distribution of mass within these regions shows that the process of gravitational decay continues. This means that even now, the M16 has not yet completed its primary mission. In its depths, new generations of stars continue to be born, which will be the last before the final dispersion of the nebula. This is where one of the most interesting unsolved mysteries arises. There is still no definitive answer as to what exactly determines the number of future stars inside such molecular clouds. Why does one dense core turn into a massive star and a neighboring one into only a small luminary? Why do some areas suddenly stop collapsing despite a sufficient supply of matter? What role do magnetic fields, turbulence, cosmic rays, and the complex chemistry of the interstellar medium play in this? Each new stage of research reveals only part of the picture, leaving more and more questions about the mechanisms of star formation. That is why the Eagle Nebula remains not just a beautiful object against the backdrop of the Milky Way. It is one of the most complex and dynamic regions of our galaxy, where almost all the key processes that determine the evolution of stellar matter can be observed simultaneously. Here, the past, present, and future are intertwined in a single cosmic cycle, which has been going on for millions of years and will change the appearance of this amazing corner of the universe for a long time to come.